Uh, Welcome back to this problem solving session for the NPTEL course Foundation Engineering. So, in the last uh, few weeks, we were solving a couple of problems regarding file foundation. So, how to determine the safe loop carrying capacity of single file, group files, and the supplement of group of files for uh, different types of soils, cohesionless soil, cohesive soil, and for different geometries of pile, that is pile with uniform shaft and underlying piles. Okay, so this week we uh, started learning a new topic, that is lateral abrasion. So as you know that lateral abrasion can be of three types. So first of all, earth pressure at rest, then active earth pressure and passive earth pressure. So earth pressure at rest, so just about a brief explanation about all these terms. So I hope you know about retaining wall. So retaining wall, this is a geotechnical structure. Okay, so this is a geotechnical structure which is used to retain some backfill. Okay, so backfill, this is another terminology in geotechnical engineering. So this is the retained soil mass. So this is the retained soil mass which is called backfill. And this is the structure. This is known as retaining wall. So this wall is basically retaining this backfill or soil mass. That's why this is called retaining wall. Now, this retaining wall is subjected to some pressure. So pressure from the backfill. Okay. So this is mostly lateral pressure. Now this lateral pressure, as mentioned, that it can be of three types: earth pressure at rest, active earth pressure, and passive earth pressure. So depending on the movement of this wall, this pressure is categorized into these groups. So first of all, when there is no movement, so if the wall is very rigid, so this wall is very rigid, and that's why due to the application or due to the pressure which is exerted by the soil, it's not moving. So there is no movement. Okay, so movement can be of in the form of sliding, rotation. So suppose this is sliding movement. So as if the wall is basically sliding in the outward direction or away from the backfill. So there is no such sliding due to the very rigidity of the structure. So in that condition, whatever pressure will be generated on the backside of this wall, that is called earth pressure at rest. Now, if the wall moves away from the backfill, so these are the two directions. So this direction is towards the backfill, and this direction known as away from the backfill. Now, if such scenario arises when the wall is basically moving away from the backfill, so in that condition, whatever pressure will be generated, so that is known as active earth pressure, and the opposite scenario, that is when the backfill is moving towards the backfill, this is known as passive earth pressure. Okay, so this is a very little explanation or brief explanation about all these three terminologies. Now, utilizing this Rankine's earth pressure theory, or based on this Rankine earth pressure theory, this we can basically figure out, or we can basically determine the distribution of this pressure and subsequently the resultant of this pressure on this wall, and for various backfill conditions like cohesionless backfill, cohesive backfill, when this backfill is basically dry with no surcharge, with surcharge, or the backfill is submerged, then the backfill is not basically the top surface of the backfill is not horizontal or level. Okay, instead it's having some inclined surface, or the backfill is not basically a homogeneous deposit. Instead the backfill is basically some layered deposit. So on the top you are having some layer, and at the bottom you are having some different layers, so stratified like deposit. So considering all these cases, we can determine the active earth pressure distribution and passive earth pressure distribution behind the wall based on Rankine's theory of earth pressure. So we'll see how to determine that distribution considering this theory. And subsequently, we have also learned about the critical depth concept, critical depth of a vertical cut, which is specifically applicable or valid for a purely cohesive backfill. Okay, and what is the distribution of active earth pressure before and after the occurrence of tension crack in cohesive backfill. So we have some knowledge about this tension crack in the earlier discussion or in one of previous sessions. So in this week, or in this through this numerical problem solving session, we'll basically learn about some more details about this occurrence of tension crack in cohesive backfill, and how this occurrence of tension crack impact or influence the active earth pressure distribution behind the wall before and after its occurrence. That also we'll see. Okay. So we'll start this session with this problem. So problem 1, it's about a retaining wall which is 6 meters high, and it's basically restrained from yielding. Now it's asked in this problem that what will be the at rest earth pressure at a depth of 4.5 meter per meter length of the wall. So this is the backfill properties. These are the backfill properties. So the backfill is having Poisson's ratio 0.35 and the unit weight 17 kilonewton per meter cube. Okay. So if we draw the backfill, the geometry of the backfill, so this is something like this. So this is the total height of the retaining wall, that is 6 meter. Okay, and we have to determine the at rest earth pressure behind the wall. So something at a depth of 4.5 meter from the ground surface. Now the backfill properties are, so Poisson's ratio 0.35 and the unit weight 17 kilonewton per meter cube. So it's mentioned in this problem that this retaining wall is basically restrained from yielding. So there is no yielding of the retaining wall, means there is no movement of the retaining wall, and that's why you were asked to determine the at rest earth pressure, because in such scenarios or in such conditions, this at rest earth pressure will be the valid earth pressure. So we have seen 3 types of earth pressure: at rest, active and passive. So this will be the applicable entity in this case. Okay, so at rest earth pressure. Now as we have seen that for at rest earth pressure, since there is no movement of the backfill, there is no movement of the retaining wall, so therefore your horizontal strain should become 0. Okay, so this is for at rest conditions, or when the retaining wall is restrained from yielding. Okay, so this is for no yielding case, no yielding of the wall. So that means your horizontal strain should be 0. Now how we can determine the horizontal strain? Suppose we are considering some element, okay, here some soil element. Now how we can determine the horizontal strain? So we can determine the horizontal strain if we know the elasticity modulus. Okay, so it's simply in this way. So this is sigma h, the horizontal stress, divided by the elasticity modulus minus mu times sigma h plus sigma v divided by E equated to 0. So here basically a soil element, sorry, so this type of soil element is basically considered. Now this soil element, so since this is a two-dimensional view, so as you can see, this soil element is basically subjected to three stresses, okay, along three directions. So first of all, this is subjected to some vertical stress due to the vertical overburden or self weight of the soil, which is basically above this element, and it's subjected to horizontal stresses into two directions, okay, along two horizontal directions. So if we consider these vertical directions as z, so this is your x and this is your y, okay, something like this. So z, this is along the height of the retaining wall, and x and y along to this direction. So I am marking here. So this is your y, this is your x, and this is your z. Okay, so if this is the three-dimensional Cartesian coordinate system, so then this should be the three stresses. Okay, someone has raised something. Can you please solve this question? 11-meter high retaining wall supports a two-layered cohesionless backfill. Properties are given below. The water table is at a depth of 4 meters from the top of the wall. In backfill side, find out the total lateral force per unit length of the wall that would act on the wall if the wall is in active condition. Okay. Okay, so I don't know this question is from is it from the assignment question, means this week assignment question or not? Since we are, so is this from this week assignment question, means week 9 or maybe week 10?
Yes, sir. This is assignment question number 5.
Okay, so then it's for your kind information that we are strictly instructed that we should not discuss about the solution of any active assignment question. We may discuss about the approach or similar kind of problem, but we cannot solve directly the problem with the data which are given to you. Okay, so I am extremely sorry because it's as per the instruction which we have received from the NPTEL office. So rather we'll solve a few similar kind of problems, means what you are telling about, that it's a two-layered backfill and each of this layer is basically cohesionless and there is a water table at the maybe at the interface of these two layers. So similar kind of question will basically solve in this week, but in that case instead of two cohesionless layers, we'll be having one cohesionless layer and another cohesive frictional layer, okay, at the top and at the bottom. So first we'll see how this problem is solved, problem 1, and one by one we'll solve those problems, okay. Okay. Okay, so if this is the scenario that the soil element is subjected to three stresses: vertical stress along the vertical direction and two horizontal stresses along the horizontal direction. So this will be the horizontal strain.
Excuse me, sir.
Huh,
Sir, can you draw the diagram only for this question?
which one?
The question which is written in the chat box.
Uh, what are you telling about? I didn't get you. So
Sir, I am saying that can you only able to draw the diagram of this question?
diagram of the problem or diagram of the active earth pressure distribution?
Diagram of the question only.
So I think you may get it from the portal, na? So something like that.
No, sir. Sir, I have confusion here that because the hair is two layer and the water table is not in the same layer because water table is in 4 meter height and the first layer is at a height of 8 meter height. So there is a little confusion only.
No, what I have got from this chat box, so where the water table is basically at a depth of 4 meter. Okay, so it's in between it's in between somewhere in the first layer. Okay, so earlier I have mentioned it wrongly that it's at the interface of the two layers. So the interface is at a depth of 8 meter from the top of the wall, whereas the water table is at a depth of 4 meter. That is at the mid depth of the first layer or the topmost layer. Okay, so there should not be any confusion because as given in the assignment, so you basically solve accordingly. Okay. Whatever data or whatever information is given to you in the assignment question, so you solve accordingly with those data. Okay. Okay, now we'll concentrate on this problem. So in this problem, so for determining the at least earth pressure, we have to consider the no yielding of the wall. That means the horizontal strain should be 0, and horizontal strain we can determine in this way. Now we'll simplify this equation. Okay, so if we simplify this equation, then the ratio of this sigma h divided by sigma b, it would become mu upon 1 minus mu. And as you know, this ratio is known as coefficient of earth pressure, obviously at rest condition. Okay, so this is coefficient of earth pressure at rest condition. So therefore, we can easily determine this coefficient of earth pressure for at rest condition since the Poisson's ratio of the soil is given to us. So what will be the coefficient of earth pressure? Please calculate and let me know what should be the coefficient of earth pressure for this problem. So it would be 0.35 divided by 1 minus 0.35. So that means what would be the value? 0.35 divided by 0.65, so that means 0.54. Okay. Now our target or aim is to determine or is to figure out the distribution of sigma h, rather the value of sigma h at a depth of 4.5 meter. Now if we know the vertical stress at a depth of 4.5 meter, and this k0 value would be basically constant since this is a homogeneous backfill. So therefore we can easily calculate the horizontal stress at a depth of 4.5 meter. So sigma h, this should be k0 times sigma v. Now this sigma v this can be calculated in this fashion: gamma times into z. Sigma v is nothing but the vertical stress, which is basically resulted from the overburden pressure, or which is resulted from the unit weight or the self weight of the soil above this depth or above this level. Okay, so that means if we basically calculate z from the top of the backfill, therefore this would be the vertical stress would be gamma times z. Gamma is the unit weight of the soil and z is the concerned level, at what level you are basically determining the vertical stress. So right now we are determining the vertical stress at a depth of 4.5 meter. So this value is basically 4.5 meter, and this gamma value is given as 17 kilonewton per meter cube. Okay, so we'll basically substitute these values and we'll determine. So sigma h, so this would be 0.54 multiplied by 17 multiplied by 4.5. So 0.54 into 17 into 4.5. So this will give you a horizontal stress or lateral pressure or at rest earth pressure of magnitude 41.3 kilonewton per meter square at z equals to 4.5 meter. Okay, so this is the answer. Okay, now can you please tell me, instead of Poisson's ratio value, if the friction angle of the soil is given to you, instead of Poisson's ratio, so if the friction angle, suppose the backfill is basically cohesionless in nature and the angle of internal friction of the soil is given to you, then what would be the approach to determine this at rest earth pressure at a depth of 4.5 meter per meter length of the wall? Okay, so instead of Poisson's ratio, if angle of internal friction is given to you, so there is one empirical relation which is given by Jackie. Okay, so I hope in 1974 that this coefficient of earth pressure at rest you can also determine in this fashion, that is 1 minus sin phi. Okay, so instead of this mu upon 1 minus mu expression, you can use this empirical correlation that a0 can be calculated 1 minus sin phi. So phi you know because it's given to you, so therefore you can easily determine the k0 value, and this k0 value if you multiply with the vertical stress at that level, you can easily determine the lateral pressure at rest at that level. Okay, okay, so in the exam, so instead of Poisson's ratio you may expect the angle of friction of the swell. Okay. Now,
सर
हाँ
सर जैसे कि आप जेड इक्वल टू 4.5 जो लिए ना सर,
हाँ
वो सर कैसे पता चला कि जेड इक्वल टू 4.5 पे हमें फाइंड करना है, वो मतलब आउट प्रेशर पे?
it's mentioned in the problem statement na, what will be the at rest earth pressure at a depth of 4.5 meter.
इसलिए मतलब 4.5 भी ले
हाँ
मतलब लेना पड़ा।
हाँ okay. Okay, now we'll take one problem from GATE examination 2018. So a vertical cut is to be made in saturated clay with cohesion 18 kPa and angle of internal friction 0 degree, unit weight 16 kilonewton per meter cube. So what is the theoretical depth to which the clay can be excavated without side collapse? Okay, now the fundamental basis for solving this problem lies in the determination of the active earth pressure distribution behind the wall, which is basically retaining this purely cohesive soil. Okay, so first we'll see what would be the active earth pressure distribution for a purely cohesive backfill. So this is the top surface and this is the reference line for Z. Now this expression between the major and minor principal stresses you can derive from the Mohr Coulomb Phelan envelope that sigma 1 should be sigma 3 tan square 45 degree plus pi by 2 plus 2c tan 45 degree plus pi by 2. This relationship between where sigma 1 is the major principal stress and sigma 3 is the minor principal stress. Now what do you mean by major and minor principal stress? What are the definitions of major and minor principal stress? Okay, first let me know what is the definition of principal stress.
It's like in the vertical line. जो का मतलब जो कर्व में जितना होके जो लाइन क्रॉस पास होता है उसी लाइन से क्रॉस होता है नॉर्मल.
Okay, so these are the stresses basically on the plane where shear stress is 0. So principal stresses are the stresses which are acting, the normal stresses which are acting on the principal plane. Now what is meant by principal plane? So principal plane is a plane where shear stress becomes 0. Okay, so in a three-dimensional problem, or right now we are dealing with two-dimensional problem. So in a two-dimensional problems, we will be having two different principal stress direction, and the perpendicular to that direction will be having two principal planes, and the normal stresses which are acting on these two planes, those are defined as principal stresses. Now the maximum of these two principal stress will give you the major principal stress, and the minimum of these two will give you the minor principal stress. Now since this retaining wall problem, we'll discuss about that later on. So first let me draw the Mohr Coulomb failure envelope for a cohesive frictional soil. Okay, so you must know this concept from the basic soil mechanics. Okay, so this is the shear stress and this is the normal stress, and this is the Mohr Coulomb failure envelope where this intercept is basically is giving you the cohesion, and this inclination with the horizontal axis will give you the angle of internal friction. So which are two shear strength properties of a soil. Now you know that after performing laboratory triaxial test, you can determine this envelope first, and from this envelope you can determine the value of C and phi. Okay, so for that you have to basically perform a series of triaxial tests, or at least 3 triaxial tests you should perform. Now after performing this triaxial test, you have to plot the Mohr circle, and after plotting the Mohr circles you have to basically draw a base fit tangent. Okay, so which will be basically tangent to all these Mohr circles. Suppose I am considering another Mohr circle, then another Mohr circle, so a common tangent basically you have to draw. Now suppose I am drawing one of such Mohr circle. So now please concentrate on these 2 points. Okay, so this point, the state of stress at this point will give you the major principal stress, and here so it will give you the this sigma, this point will give you the minor principal stress, and this value, this point will give you the major principal stress. Why? Because at these 2 points, as you can see from this plot, the tau becomes 0. So at this point, suppose this is point A and this is point B. So both these points, the shear stress value would become 0. So from the basic definition, the normal stresses at these points will be principal stresses, and the maximum of these two will give you the major principal one, and minor of these two will give you the minor principal one. Now we can basically go for some geometric relationship. Okay, so this will become a tangent, this will become a basically triangle. So this is, suppose we are denoting the center of the Mohs circle as O, and this is as C. Okay, C we are already we have basically used it for cohesion, so we are taking some different notation, suppose E, and this is suppose A. So this OEA, so it's basically forming a triangle. Now from this OEA, since you know that this radius will be basically perpendicular to this tangent EF at point E. So therefore, from this triangle, you can define the value of sine phi. So this is basically phi. So you can basically define the sine phi as, how you can define the sine phi? Sine phi, this is the perpendicular by
OE by OF.
OE by OF. Very good. Very good. OE by OF. Now, what is the value of OE? What is the value of OE in terms of principal stresses? OE means the radius of the Mohs circle.
Radius sigma 1 minus sigma 3 by 2.
Sigma 1 by sigma 3 by 2. Very good. And what is the value of OF? What should be the value of OF?
Sigma 1 plus sigma 3 by 2.
No. Sigma 1 plus sigma 3 by 2, it would be from the origin of this two-dimensional plot. Okay, so that means if we basically take a point here, suppose this point is basically P, which is at the origin. So OP, additionally you have to consider this FP. So this would be FP plus PO. Now PO, you can basically substitute the value of PO as sigma 1 plus sigma 3 by 2. Now what is about the FP? How we can get the value of FP? So FP we can get again from the small triangle, this triangle, because this intercept is your C and this value is your phi. So you can determine this FP as C cot phi from the basic geometry, simple geometry. This is your C, this angle is your phi. So this value basically C by FP will give you the tan phi, perpendicular by base. So therefore FP will be simply C cot phi. Now if we substitute all these values in the previous equation, so it will basically become C cot phi plus sigma 1 plus sigma 3 by 2. Okay, so this is the expression for sine phi. Now if you basically go for some algebraic manipulation, then at the end you will be having the final expression as sigma 1 equals to sigma 3 tan square 45 plus 5 by 2 plus 2c tan 45 degree plus 5 by 2, whatever or already which I have written at the beginning. Okay, so this expression you will be having after the algebraic manipulation of this expression of sine phi. So this is the root or fundamental basis of this expression. Okay, so though this is not needed, for solving this kind of problem. Okay. However, for a broader perspective, I am explaining a little bit about this. Okay. Now we'll basically consider the active condition, since I have mentioned that to determine the theoretical depth of a vertical curve, we should first know about the active earth pressure distribution in a purely cohesive soil. Now for active condition, so since there are two principal stresses, one is major, another one is minor. Now for active condition, which stress? So in a retaining wall problem, just now we have seen, so two stresses are involved for a two-dimensional problem. The first one is sigma v, vertical stress, and the next one is horizontal stress, which is nothing but the lateral earth pressure. Now for active condition, which one be the major principal stress here? Out of horizontal and vertical stresses, which one become the major principal stress and which one would become the minor principal stress considering active condition?
Gamma V is minor or gamma H is major, sir?
Gamma? Okay, you are basically telling in terms of the value when sigma v, which whatever value it will basically assume. So on the basis of that, you are
एक्टिंग वैसे एक्टिंग फोर्स जो वो होता है ना सर,
हाँ
जो लेटरल फोर्स
हाँ
एक्टिंग करता है मतलब एक्टिव कंडीशन में सर,
हाँ
तो जो गामा एच है जो हॉरिजॉन्टल जो फोर्स है ना सर,
हाँ
वो ज्यादा सर मेजर सर है, वो मैंने बोला सर.
okay. No, I think were in the line, but however, I don't know. So suppose this is the again mode Coulomb failure envelope C and pi. So first we can draw the Moore circle considering the
Sir,
at rest condition.
I have doubt here, sir.
Sir,
Sir, at the point C, where you have put the point C in the above diagram. From the left side, why you have put the vertical line towards the circle? Why you have not put it at the C?
I didn't get you. Means you are trying to say that this vertical line I should draw in this location?
Yes, sir. Yes, sir. What is the reason behind it?
Because the soil is cohesive frictional. So you will only get the what is the meaning of this diagram. So instead of this line, if we basically draw the line, or you are basically shifting the origin of the plot. So earlier the origin was at this point, okay, at this point. Now you are having the origin at some different point. Now I will explain, sir, what is the difference between these two plots.
Repeat once again, sir. Why we have put it there? Repeat once again.
We are not basically putting the vertical line. These axes are basically constant. This is basically your x-axis, this is your y-axis. So we are not basically playing with the axis. So this is your origin, okay, this is 0 0. So where the x-axis basically along x-axis sigma n normal stress is plotted, and along y-axis shear stress is plotted, okay, and this is the origin. Now for a cohesive frictional soil, the soil is having both cohesion as well as angle of internal friction. That means for a C5 soil, the Moore Coulomb or shear strength envelope should become like this, and the gradient of this line will give you the friction, and the intercept value along the y-axis will give you the, or along the shear stress axis will give you the cohesion. Now If this is not the case, what you are trying to say, suppose you are having this kind of plot. So this is the more Coulomb shear envelope. Now what does it signify? So it signifies that the shear strength envelope is now passing through the origin of the plot. So origin of the plot means there is no cohesion, there is no intercept. So that means there is no cohesion. Cohesion is now 0. Now if cohesion is 0, so that means the soil for which you are plotting this MC envelope, that is basically purely what? Purely cohesionless. Are you getting my point?
Yes, sir. Yes, sir. I'm getting.
Now what will be the plot shear strength envelope for a purely cohesive soil? What is your guess? For purely cohesive soil, what will be the plot? Or rather I can say, how does it look like for a purely cohesive soil? So this is for C5. So the soil is having both the shear strength components, cohesion as well as friction. Here the soil is not having any cohesion, only angle of internal friction. Now if the soil is having only cohesion, no angle of internal friction, like this problem, here the soil is having only cohesion, no internal friction. Now how the shear strength envelope look like? How does the shear strength envelope look like? So it will look like a horizontal line which is parallel to the sigma n axis. So that means the gradient phi is now 0. However, there is a intercept, cohesion intercept along the shear stress axis. Is it clear? So this MC envelope will change as per the type of soil. Okay. However, this origin, this is constant. We are not changing the origin. Okay, I hope it's clear now. Now we'll concentrate on the sigma 1 and sigma 3 values for active condition. Now we'll basically have some idea about the active condition. Okay, so how it's basically generated. So we'll start from the at rest condition. Though I think you should know from this, if you go through the lecture material. So this is the MC envelope, and right now I am drawing considering the generalized scenario that soil is having both C and phi components. Okay, so this is the Mohr circle considering at rest condition. Is considering at rest condition. So this value would be your sigma H naught, and this value would be your sigma V. Now sigma V for a particular depth or for a particular level, you can get from a product of unit weight of the soil and the respective depth of the layer. Now this is gamma Z. Now this gamma Z will not change. For to active condition, to prevail the active condition, what is the condition? That your backfill should move away from the backfill. Oh, sorry, your retaining wall should move away from the backfill. That means in this direction. Okay, in the arrow which I have basically shown in this slide. So away from the backfill, the retaining wall should move. Now if the retaining wall moves away from the backfill, so your sigma B for a particular level, okay, so suppose this is the level, so at this level your sigma B will not change, gamma Z will remain constant. Now what will be the change? So change will be in the horizontal stress component. So how it will change? So it will basically try to reduce. So it will basically reduce. Now if the sigma H0 value will try to reduce, now how this Mohr circle will change? So the Mohr circle will basically shift in the left direction. Okay, so as the retaining wall is moving away from the backfill, your horizontal stress is basically reducing. Now a moment will arise. Okay, so my drawing is not very good, So a moment will arise when it will basically touch the molecular failure envelope. Now this horizontal stress will give you the active earth pressure behind the wall at that level. Since this space, the soil cannot exist above the morculum failure envelope. This is the limit. This morculum failure envelope is basically defining the limit. So the morculum or the Mohr circle, which is basically touching the morculum envelope, so this stress will give you the horizontal the lateral earth pressure corresponding to active condition. Now for the passive condition, it's a opposite scenario. So the circle will basically grow in the reverse direction. So where the vertical stress will again remain constant, however the horizontal stress will basically increase. Okay, so at a moment will basically arise. So at this moment, this Mohr circle will basically touch the morculum failure envelope, and considering this circle, this horizontal stress, this value will basically give you the passive earth pressure. Now tell me from this plot, so considering the active condition, which value is bigger? Sigma HA is bigger than sigma B, means sigma HA is greater than sigma B, or sigma HA is less than sigma B?
Sigma HA is less than sigma B.
Sigma HA is less than sigma B. And what are these two values? These two values are nothing but the principal stresses. So now which one would become the major principal stress for the active condition, and which one would become the minor principal stress for this active condition? So sigma HA, the minimum
Sigma
of these
B.
two. Now sigma B is greater than sigma HA. Na? So sigma B will give you the major principal stress, and sigma HA will give you the minor principal stress. Am I correct?
Yes, sir.
And for passive condition, it will be the opposite. Sigma B will give you the minor principal stress, and sigma HP, that is the lateral pressure, will give you the major principal stress. Okay, so it should be clear. So since this sigma 1, so this sigma 1, so for active condition, this sigma 1 would be sigma B, and sigma 3 would be sigma HA. And our concern is to draw the distribution of the sigma HA along the height of the wall. So sigma HA, so we can write, after simplifying this equation, that sigma B tan square 45 degree minus 5 by 2 minus 2c tan of 45 minus 5 by 2. Okay, now this is, you can consider as Ka, that is the earth pressure coefficient as at active condition, or with respect to the active condition. So sigma B Ka minus 2c root under K. Again sigma B, you can write the product of unit weight of the soil and the height or depth. So gamma zk minus 2c root K. So this is the variation in active earth pressure with the depth z. Is it clear? So in this way, we have basically got the distribution or the variation in active earth pressure with depth z, and this z is basically measured from the top of the wall. Now, huh?
Means that sir, मतलब इस क्वेश्चन में फर्स्ट हमें मतलब वो पहचानना पड़ेगा, मतलब कौन सा मेजर है और कौन सा मैनर है वो फाइंड आउट करना पड़ेगा, उसके बाद वो वाला फॉर्मूला लगाना है, वो है ना सर?
हाँ, this is the backbone equation. Now concerning the active or passive condition, you have to basically appropriately or suitably substitute the values of sigma 1 and sigma 3. Then only you can get the distribution of sigma HA. Otherwise, you have to memorize this equation. This equation you have to memorize. Okay. Okay. Now, if this is the variation in active earth pressure along the depth of the or height of the wall, then what will be the active earth pressure at a depth at the top surface of the wall? At the top of the wall, what would be the active earth pressure? At the top of the wall means at z equals to 0. Now at z equals to 0, what would be the active earth pressure? So this value would become 0, na? Since z is 0. So this second term will only be there. So therefore, this sigma HA, this will be minus 2c root A. Now as you can see, you are basically having some negative pressure. So if this is the wall, so you are basically having some negative pressure. Okay. So some negative pressure induced at the top of the layer or top of the backfill. So this is your backfill surface. So you are having some basically tension at the top. Now if you go below, okay, now if you go below, suppose you are increasing the z value. So at some level, at z equals to z0, what will happen? This sigma HA would become 0. So it will basically intersect this axis. So it will become 0. Now if you further go down below, that means z greater than z0. Now you will be having positive lateral earth pressure. So you will be having the distribution something like this. So this is for only for cohesive frictional soil. So if you consider purely cohesionless soil, this C component will not be there. It will be 0. So therefore, there is no condition of tension at the top of the wall. There is no generation of tension at the top of the wall. So this is only valid. This phenomena of tension crack is only valid for a purely for a cohesive frictional soil or purely cohesive soil. Okay. Now, if this is Z0 and this value is minus 2c root Ka. Now, if you go down from this point of inflection, if you go down by a depth of again Z0, so this value you will get, again 2c but plus 2c root under Ka. Now, if you basically try to calculate the resultant of these two, that means the resultant of this portion. So where the resultant you can determine from the area of this triangle and it will act in this direction, and for the bottom triangle it will act in this direction. So these two resultant, or rather you can say the resultant of this distribution of active earth pressure for a total height of or total depth of 2z0, z0 plus z0, it will basically will be what? It will be null. This negative pressure will be counterbalanced by this positive pressure. This negative and positive will be basically will nullify each other. So therefore, as if there is no pressure on the wall, there is no resultant lateral pressure on this wall. So for this portion, at least for this portion, okay, for a height of 2z0. Now if there is no pressure from the soil on this wall, so then there is no need to support this support this soil. So when you will basically excavate a soil, so you basically need to provide some lateral support so that the side soil doesn't collapse inside the excavation. So when you go for some excavation, you need to provide some lateral support to basically resist the lateral movement of this side soil, so that the side soil should not collapse inside the excavation. Now, as you can see, at least for a depth of 2Z0, you can safely carry on the excavation. There is no need to provide any lateral support, or the soil should not collapse. Okay, the side soil should not collapse. And that was the yeah. Someone is having some query. You can ask me.
Sir,
Huh.
in this figure or in this picture,
Hmm.
at what distance the force is acting from the base?
At what distance the force is acting? So means which force? The resultant of this total distribution or the resultant of this individual distribution? Total distribution. For that you have to take the resultant and the moment. You have to basically take the moment of this individual component, and then you can easily determine this the lever arm of this distribution. We'll see, we'll be having similar kind of problem, okay, in the subsequent slides. We'll see how to determine the location of a resultant with respect to the base of the wall. Okay.
No, sir. For the same question, can we identify that once?
Why not? We can easily determine.
Okay, sir.
Suppose
Please do, sir.
Suppose this is your reference line. So with respect to this bottom line, you try to determine the location of the resultant earth pressure. Now what you have to do, you have to basically consider these two triangle individually. Now first of all, you know the base and height of this triangle, and you know the base and height of this triangle. Okay, so right now I am considering the area of this triangle is A1 and area of this triangle is A2. Okay, since we didn't go up to that part. Now the A1, that means the resultant pressure is basically acting at a height of Z1 bar, and this resultant is basically acting at a height of Z2 bar. Now how we can figure out this Z1 bar and Z2 bar? It's very simple, very straightforward. Since you know that the resultant of this triangular distribution will basically act at the CG of this geometry. That means you should know the CG of a triangle, for at least for this problem. The CG of this triangle you should know about this base, and CG of this triangle you should know about this base. So you know A1, A2, you know Z1 and Z1 bar and Z2 bar. So the resultant of this entire distribution, suppose it's basically acting at a height of Z bar. So Z bar resultant multiplied by Z bar, this will be A2 Z2 bar minus A1 Z1 bar. Okay.
Sir, what is the height of Z1 bar?
Z1 bar just now I have described, na? Z1 bar, this is the CG of this triangle with respect to the base. Now what is the CG? What is the CG? What is the location of a CG for a triangle?
1/3 of the triangle.
1/3 of triangle, but from which side? Which one? Suppose this is the triangle, this is the height. Now you are telling me that the CG will lie at a height of h by 3. Now from which side? From this side, from the base, or from the apex?
I think from the base.
From the base, this is h by 3. Okay. Now for this condition, it will be from the apex. So from the apex, if we determine, then it will be 2 h by 3. Suppose we are denoting this height as a small h. So 2h by 3 plus this height you have to additionally add. Okay. So this is your basically 2h by 3. Now if you add this height with this 2h by 3, you will get the final height with respect to the base. Is it okay? Huh?
Yes, sir.
So this is the triangle. Okay, so this is the triangle. Now we are trying to determine the resultant of this triangular distribution with respect to the base. Okay, now this height is z0, that is the tension crack depth. Now what is this height? This height is h minus z0. Why h minus z0? Because the total height of the retaining wall h, and that value we should know, because you can ask me how we should know about this capital H. So capital H is basically given to you, that is the known height of the retaining wall, and this z0 value you can figure out. We'll see how to figure out this z0. Right now you assume that you know the value of z0. Now how we can determine the resultant of this distribution z1 bar from the base? So z1 bar, it would be 2z0 by 3. So from this apex, this distance should be 2z0 by 3 plus h minus z0.
And for the Z0, sir, the Z by 3. The height of a Z0 is capital Z by 3.
Which one?
Z0.
Z0, right now I am telling you, na, you should assume the Z0 value for this part, because Z0 we didn't basically go up to that part, how to calculate the Z0. We were in the process, okay, how to calculate the value of Z0. Okay, now may I go further?
Yes, sir.
Okay. So earlier we were discussing about the distribution of active earth pressure behind a retaining wall, which is basically retaining a cohesive frictional backfill. Now for this cohesive frictional backfill, at the top of the layer or at the top of the retaining wall, you may encounter some tension, and as you go below in the backfill, so this tension will basically positive. Okay, so some at the top of the layer or at the top of the backfill, for certain portion you will be some negative earth pressure distribution, and then it will basically become positive as you go down inside the backfill. And consequently, for a depth of 2 times z0 from the backfill surface, you will be having no resultant pressure, and this indicates or this signifies that you should safely carry out a vertical excavation without any side collapse, because there is no resultant lateral pressure acting on the soil or exerted from the backfill. And this is asked in this question: what is the theoretical depth to which the clay can be excavated without side collapse? So our answer to this question would be that we can safely excavate, or the theoretical depth to which the excavation we can safely carry on, so that depth will be 2 times z0. And why? Just now we have explained. Okay, so this is the critical height of a vertical excavation without any side collapse or without the requirement of any lateral support. Now, as you asked, how to calculate this z0? Now, the fundamental for the calculation of this z0 lies in this equation, that at z equals to z0, the lateral earth pressure should become 0. Okay. So we have basically assumed this depth Z0. Z0 basically is the depth at which the lateral earth pressure is becoming 0. Now, if this is the scenario, then gamma Z0 Ka minus 2c times root under Ka should be 0, because this is the expression of the sigma h. Here we are basically substituting the value of Z0. Yes or no? This is the expression of the active earth pressure behind the wall. Already we have derived, and here we are substituting the value of Z0. For that, this sigma h would become 0. So therefore, gamma Z0 times Ka minus 2c times root under Ka should become 0. So obviously, this Z0 would become 2c by gamma times root Ka. So if you basically simplify this equation further, then you will get the value for Z0 as 2 times cohesion divided by unit weight multiplied by root under active earth pressure coefficient. Is it fine? Yes or no?
Yes.
Okay. Okay, now Ka already we have determined, we have basically defined that this is the Ka, tan square 45 degree minus 5 by 2. Now for this problem, since phi is equal to 0, so K value would be simply tan square 45 degree, so that means 1. What is the value of cohesion for this problem? So the value of cohesion is 18 kPa. Okay. And what is the value of unit weight? So gamma is basically 16 kilonewton per meter cube. Now you have to just substitute these values in this equation so that you can calculate the value of critical height of the vertical excavation or critical depth of vertical excavation. So here it's 2 times Z0, and Z0 already 2 times cohesion by gamma root K. So that means finally it would become 4 times cohesion divided by gamma root K. Okay. Now you substitute the values and let me know the final value for HCF. Please substitute the values. So I am getting this value as 4.
4.5.
हेलो
Yeah.
सर सी का वैल्यू नहीं दिया होगा इसमें तो कैसे फाइंड करेंगे?
No, it should be given. Otherwise, you cannot solve this problem. If you don't know the properties of the soil, then you cannot solve this problem. Okay. So for solving this problem, you should have the cohesion value and it should be provided. So you should not worry about that. Okay. Anything else? Okay, I am assuming it's perfectly fine from your end. So I will move further. Now we'll take problem 3. So this is related to the previous problem, that is problem 2. The retaining wall supporting a C5 soil backfill moves slightly away from the backfill. That means it's talking about the active earth pressure condition. Under this condition, at a particular depth Z0, there is no earth pressure acting on the wall, which just now we have seen. Okay. So at a particular depth Z0, there is no earth pressure acting on the wall.
हेलो एक्सक्यूज मी सर,
Huh.
सर दूसरा क्वेश्चन में सी का वैल्यू नहीं दिया है, तो सर कैसे फाइंड करेंगे सर? कोई तो मेथड होगा ना, कोई फार्मूला?
No, it should be given to you. Just now I have replied, na?
नहीं सर, दूसरा क्वेश्चन में है ना असाइनमेंट का क्वेश्चन, उसमें नहीं दिया है सी का वैल्यू, तो कैसे फाइंड करे वो मुझे बता।
So you are asking about the second question in assignment. Hello?
यस सर।
So you are basically asking about the second question in the assignment of the assignment. So I don't have any idea about the assignment question. So can you please repeat?
ओके सर, ठीक।
Okay. So as per my understanding, it should be complete, and I hope it's complete. Okay. So all the necessary information which you should require to solve the problem already given to you. So in any case you are having any doubts while you are solving the problem, that there is no data which you should require to solve the problem, that means any kind of data insufficiency you are feeling to solve the problem, you can please write in the Google forum. Okay, so you can make use of the Google forum to basically raise your concern. So I will request all of you, if you are feeling any kind of data insufficiency, so you please write in the Google forum. Okay, so our NPTEL team member, they will basically see and let you know about the further or subsequent actions. Okay, okay, right now we'll basically try to solve this problem 3, and it's interconnected or interlinked with the previous problem. So where it's mentioned that at a particular depth there is no earth pressure acting on the wall. The more circles for the state of stresses at this particular point would be. Now 4 options are given to you, that concerning this point, the point which is at a particular depth z0, what is the best representation of the state of stress at this point? So a point, it will be a point circle at a distance gamma z0 from the origin towards the positive x-axis. Okay, so I am drawing all the 4 options. So this is the tau sigma n axis, and the first option is talking about, this is a point circle at a distance gamma z0 from the origin towards the positive x-axis. So is this a point? Suppose this is point. Okay, and this is at a distance of gamma z0, a point circle in the sense it's not having any radius. So this is option A. Now what is about option B? So option B, this is a circle of diameter gamma z0. Okay, so this is a circle of gamma z0 passing through the origin and lying towards the positive x-axis. So this is talking about this kind of scenario, that this is having a diameter gamma z0, and again the circle is passing through the origin and lying towards the positive x-axis. So this is option B. Now what is in option C? So in option C, a circle of diameter gamma z0 with its center at the origin. Okay, so that means this kind of scenario. So we are having a circle of diameter gamma z0, and again the center is at the origin. That means the radius here, it would be gamma z0 by 2. And this is option C. And what is in option D? So option D, a circle of radius gamma z0 passing through the origin and lying towards the positive x-axis. So it's basically similar to option B. However, here the diameter is basically twice of that option B. Okay, so earlier the radius was gamma z0 by 2. Now here the radius is gamma z0. So that means it will be a bigger Mohr circle. Okay, this is 2 gamma Z0. Now we have to figure out the correct option. Now how we can figure out, as per your opinion, what should be the correct option? Okay, so for that you should know the major and minor principal stresses for the given condition. Now as you can see, since this is a point, what does it represent? So it represents that the major and minor principal stresses are equal. So for that, the radius should become 0 and it becomes a point circle. So major and minor principal stresses should be equal. And what are the major and minor principal stresses for a active earth pressure condition? So as you know that active earth pressure condition, the major principal stress is nothing but the vertical stress, that is gamma z, and the minor principal stress is nothing but the lateral earth pressure, active earth pressure, and this is you can determine from the previous expression. Okay, so here I have written in the previous problem. So this is for active condition. Now as you can see, these two values, this major and minor principal stresses, are not equal. So therefore option A, this is discarded. This is not valid for this problem. Okay. Now 3 more options are left. Now we'll talk about the second option and we'll talk about the problem scenario. So where the state of stress is at a particular depth Z0. Now at a particular depth Z0, your sigma 1 would be sigma V and it would be gamma times Z0. Okay, the value of Z is given to you and it's Z0. So sigma 1, the major principal stress, would become gamma times Z0. Now what is about the minor principal stress, that is the earth pressure? So there is no earth pressure acting on the wall. That means the sigma 3 equals to sigma HA, it is 0. So these are the two values. Now considering these two values or based on these two values, please try to answer me about the correct option among these 3 options B, C and D, because the A option already we have discarded. And already we have seen that these 2 points of this Mohr circle will give you this point will give you the minor principal stress and this point will give you the major principal stress. So this state of stress sigma 1 and sigma 3 values are gamma Z0 and 0 respectively. Now which Mohr circle basically suitably represent this state of stress? Okay, so option B is the correct option. Okay, answer. Why? Because see that here the circle is basically passing through the origin. That means sigma 3 value is 0. And again the diameter of the circle, Mohr circle, is gamma Z0. So what does it represent? It represents that sigma 1 value is gamma Z0. And this is a condition given to you. Sigma 1 value gamma Z0 and sigma 3 value 0. So therefore this Mohr circle represents the given state of stress correctly or appropriately. Okay. So any confusion? Okay. So if it is fine, then we'll go further. So this is the answer. So answer is option B. And here it is shown very clearly that this is the Mohr Coulomb failure envelope for a cohesive frictional soil, and this is the Mohr circle, which is basically representing
Sir.
the given state of stress. Huh?
एक बार सर बैक कीजिए स्लाइड. Yes, sir.
Okay. Okay.
Sir, I have one question.
Huh.
मतलब little confusion, sir. Question little confusion. Sir, if there is an internal friction given angle with the internal friction is suppose something value 60 degree. That means that is a phi value or theta value.
What are you asking about? That which one?
In any question there is a given internal friction is some value. That is a phi value or a theta value.
I am not getting you. It's given as what? Angle of internal
friction.
Huh.
Yes, sir. Angle of internal friction is given as some data. That is the value of phi or a value of a theta.
Okay, I didn't mention anything about theta in this problem. So how?
So I am asking. I am not asking related about the question number.
Okay, even I don't know. Means in the lecture also there is no introduction of any variable called theta. So c and phi are the two shear strength parameters, and it's universally used. Okay, c represents the cohesion, and phi represents the angle of internal friction. So wherever you will basically get the angle of internal friction value, so that will represents the phi value only. Okay, so the angle of internal friction is always represented in terms of or using this notation phi.
And if it is inclined, that is known as the theta value.
And it's inclined.
If it is inclined somewhere, that means that data is the theta value.
See, if you are talking about the notations and the terminologies used in the problem statement, so problem to problem the notations may vary. So what you are trying to highlight, that if you are having some variable called theta, then that should be defined in the problem, or that should be related in your to your course. Okay, whatever topic which you are learning, so the variable which is given to you, that should be related to the course. And in between, in the course, you should have a clear idea about all the variables which you are dealing with. So many times after the problem statement, it's mentioned that use the usual meanings of the notations used in the problem. Are you getting my point? So after the problem statement, many times it's written that use the usual meaning of the notations used in this problem. So that means you should know this theta is used to represent the inclination of a plane. Okay. However, this theta value can be used to signify more other things as well. So that's why I am telling you that the use of these variables and notations basically vary from problem to problem. So right now we are dealing with retaining wall problem, the earth pressure problem. So therefore, the C and pi invariably will indicate the cohesion and angle of internal friction of the soil. Now, we'll see later on that inclination which you are talking about. Suppose the backfill surface is inclined to some angle. So this angle you can represent in terms of I or in terms of theta. So in some textbook you may basically encounter that I is used to notify this inclination of the backfill surface. In some other textbooks, you may encounter that theta is used to signify or this represent the inclination of this backfill. So it will be mentioned, okay, in the problem, or whatever notations, standard notations are used in the problem, you should act accordingly. Is it fine? The notations you should use as per the course. So right now we are basically concerned about the foundation engineering course. So in this course, whatever notations will be used, we'll strictly follow that notations. Okay. I hope it's clear. Okay, now we'll take another problem, and this problem is taken from GATE examination 2020. So in this problem, a 5-meter high vertical bulb has a saturated clay backfill. The saturated unit weight and cohesion of clay are 18 kilonewton per meter cube and 20 kPa respectively. The angle of internal friction of clay is 0. Okay. Okay, just a minute.
So,
Huh.
sir, first let's describe the all question. Then
हाँ, tell me.
पहले सर आप क्वेश्चन को डिस्क्राइब कर दो ना सर, उसके बाद सॉल्यूशन
Okay. So this is a 5-meter high vertical bulb, and this is having a saturated clay backfill. The saturated unit weight and cohesion of clay are 18 kilonewton per meter cube and 20 kPa respectively. The angle of internal friction of clay is 0. Now, in order to prevent development of tension zone, the height of the wall is required to be increased. Dry sand is used as backfill above the clay for the encased portion of the wall. The unit weight and angle of internal friction of sand are 16 kilonewton per meter cube and 30 degrees respectively. Assume that the back of the wall is smooth and top of the backfill is horizontal. To prevent the development of tension zone, the minimum height in meter round up to 1 decimal places by which the wall has to be raised is. Okay. So what does it tell? So it basically represents the scenario which just now we have explained. So for a cohesive frictional soil, there is a chance, or for a purely cohesive soil, there is a chance that at the top of the wall, you have a tension zone. And in the earlier session, I have mentioned that this kind of tension is not at all expected or desired in soil mechanics problem. Why? Because from the fundamentals, basic fundamentals, soil is very weak in tension. So it cannot resist tension, but however, it's good in compression. So therefore, we'll always try to avoid those kind of scenarios where there is a chance of build-up of tension pressure or the generation of tension crack. Okay. So what is the remedy to those problems? So one of those remedial measures is talked about in this problem, that a 5-meter vertical wall, it's basically retaining a clay backfill, saturated clay. So obviously there would be the active earth pressure distribution like this. So at the top part there will be negative pressure or tension, and then followed by some positive earth pressure distribution, and this depth already we have discussed about it. This is Z0, because at a depth of Z0 the pressure would become 0, the earth pressure obviously. Now we didn't expect, or we don't desire this kind of, or recommend this kind of pressure or at the top of this backfill. Now how we can eradicate this kind of problem or this kind of situation? So one such remedial measures is like, we are basically extending or increasing the height of the wall by some amount. Okay, so we are basically increasing the height. So this height, this additional height is your h, and this part is now filled with dry sand. Okay, so this part is dry sand, and this is the saturated clay. Now what we need to determine? We need to determine the minimum H minimum. Okay, so the minimum height of this H. So we can go for any height of this H, so that there should not be any tension throughout the backfill. Obviously for sand portion there should not be having any you should not worry about or bother about any tension for sand. And why? We have explained earlier. Only the chance of generation of tension crack will be in the clay portion. So we can basically provide a height so that there should not become any development of tension zone inside the backfill. However, we can optimize this height. So if we basically provide a increased height, obviously it will not be optimal case. So it will not be the optimum scenario. So for the optimum case, we should provide the minimum height so that there should not be any development of tension zone. Now, how this optimum case will arise, or what is the fundamental basis to this minimum height? So the fundamental basis of to this minimum height will be governed by the active earth pressure at this interface. Interface of what? Interface of this dry sand layer and the saturated clay layer. So you have to provide the minimum height in such a way such that the pressure should be always greater than 0 at this interface. So at most you can have a 0 pressure. Okay. Now, what is the advantage of placing this additional or minimum height which is filled by dry sand? Now, this is the equivalent problem statement. So equivalent problem statement would look like this, that whenever you will basically place a dry sand field of height H minimum on the saturated clay, so this dry sand will basically impart some uniformly distributed surcharge above the saturated clay. So this value is Q, and this Q is nothing but gamma times H minimum. Okay, gamma is the unit weight of the dry sand, and H minimum, this is the thickness of the dry sand. So this is the unit weight of the dry sand. So we know the unit weight of the dry sand as 16 kilonewton per meter cube. We have to just figure out the H minimum value so that the pressure at this interface or at the top of the saturated clay should become 0. Now, what is the distribution of active earth pressure? So the distribution of active earth pressure, sigma HA, so that you know, gamma Z Ka minus 2C Ka, and this expression is valid only for without surcharge case, when there is no surcharge. Okay. However, in this problem, we are having a uniformly distributed surcharge at the top of the saturated clay, and this surcharge value we have calculated in this fashion, gamma times H minimum. So here we are basically taking the Z from this reference line. So the reference line is at the interface of the dry sand and the saturated clay. Okay. So therefore, there will be one additional term, Q Ka, due to the application of this uniformly distributed surcharge. And this value at most should become 0. It can never be negative. So in such a way, we have to basically place the fill of dry sand. Okay, we have to decide the thickness of dry sand. So if this is 0, so therefore, and again this Z value is 0, because we have taken the reference line at the interface of the saturated clay and the dry sand. So Z is 0. So therefore, this minus 2C Ka plus gamma H minimum Ka equals to 0. So H minimum we can calculate from 2C by gamma root A. So this is the expression. Now please keep in mind that this gamma, this is for the unit weight of ricin. However, this Ka, this is for the active earth pressure coefficient for the saturated clay. Okay, we are determining the active earth pressure distribution in the saturated clay portion. This is the active earth pressure. Now you can basically input the or substitute the given inputs. So 2 times the cohesion is given as 20 kPa, then gamma of the dry sand is given as 16, and Ka value, this will be obviously 1 because for clay phi equals to 0, so Ka value equals to 1. So this value would become 40 by 16. So 40 by 16, that means 2.5 meter. So this is the answer. So minimum thickness or minimum height by which the retaining wall height should be increased, that is 2.5 meter. So if you basically provide a thickness of dry sand as 2 meter, then there is a chance of generation of negative pressure at the in the saturated clay portion. Okay, since our aim is to prevent the development of tension zone, therefore we have to go for a minimum thickness of dry sand as 2.5 meter. And if you provide more than 2.5 meter thickness, obviously the earth pressure value at the interface also will not be 0, it will be greater than 0. So this is basically this condition is basically valid for the interface. Okay, so right now we are discussing about the interface between sand and clay. Okay, so in this way you can determine the minimum height to prevent the development of tension zone, minimum height of dry sand. Is it fine? Okay, if this is so, then I will basically
Sir,
take the next problem. Yeah.
for going to the next problem, I have one question. Can you maybe some
Okay, in problem 5, a vertical retaining wall of 12 meter height, suppose
excuse me, sir. For going to question number 5, I have one question.
which one?
Question is that, sir. I have one question, sir.
For which problem? Problem 4 or problem 5?
No, no, sir. I have out of your question,
Okay.
not related.
Tell me.
सर मैं बोल रहा हूँ, आप एक सरफेस शीट ड्रॉ करके दिखा दो ना, आपने समझ नहीं आएगा क्वेश्चन.
I am not getting you fully. What you are trying to say?
सर मैं बोल रहा हूँ, आप सरफेस शीट ड्रॉ करके दिखा दो. मतलब प्रॉब्लम ये है, इसमें से क्या मतलब कैसे फाइंड करना है, मतलब अर्थ प्रेशर फाइंड करना है. ठीक है सर, सरफेस शीट आपको ड्रॉ करना है.
No. For which problem? Problem 4 or problem 5?
No sir, that is my personal problem, sir, not related to this problem 4 or 5.
So you are trying to say that I have to draw a distribution for as per your problem definition.
Yes, sir. Yes, sir.
Okay, then what is your problem definition? Can you please?
Yes, sir. Yes, sir. I am telling that, sir. Suppose 15 मीटर का एक रिटेनिंग वॉल है, ठीक है सर।
Okay.
इसमें 50 क्वेश्चनलेस सॉइल है, ठीक है सर।
Okay.
इसमें 2 लेयर है, एक लेयर है सपोज 9 मीटर के डेप्थ पे एक लेयर है।
Okay, let me draw the retaining wall first. So it's a total. It's having a total height of 15 meter.
15 मीटर, यस सर।
Yeah.
9 मीटर पे एक लेयर है।
Okay.
ये रिटेनिंग वॉल कोहेजनलेस सॉइल के लिए है, ठीक है सर।
Okay.
The height of 9 meter, yes sir. And the water table is at the depth of 7 meter.
Okay.
7 मीटर पे एक वाटर टेबल है सर।
Okay.
लेयर 1 के लिए सर,
Yeah.
लेयर 1 में सर सैचुरेटेड गामा का वैल्यू मतलब 16.5 है।
Okay.
एंड ड्राई यूनिट वेट मतलब ड्राई वाला 70.5 है, 75.5 नहीं, 17 है, 17।
Okay.
हाँ। अब मेरा क्वेश्चन अब ये है सर, जैसे कि अब मतलब फर्स्ट लेयर के लिए अगर हमें सर वो फाइंड करना होगा सर, लेटरल फोर्स फाइंड करना होगा, तो इसमें से मतलब ये दोनों के लिए अलग अलग गामा का वैल्यू रख के करना पड़ेगा कि क्या करना पड़ेगा सर? क्योंकि इसमें एक ही लेयर में तो दो ही ड्राई मतलब यूनिट वेट है, ड्राई के लिए भी और सैचुरेटेड के लिए, दोनों के लिए है। अगर हम फर्स्ट लेयर के लिए हम अगर फोर्स फाइंड करेंगे तो गामा का वैल्यू कौन से लेंगे? ये मेरा क्वेश्चन है।
Okay. So please see that since you are having the groundwater table means inside the layer 1, so it's at a depth of 7 meter from the top surface of the backfill. Now I don't know that obviously this part that means below the water table, it will be dry or in saturated condition, but
What sir? Sir, your sound is not clear, sir. Once again.
the soil mass in layer 1 under the groundwater table, it will be under saturated condition or dry condition. The
वाटर टेबल के नीचे वाला पोर्शन सर।
हाँ, below the water table, the portion of layer 1, so it will be saturated or in dry condition.
वही तो सर मुझे नहीं पता था कि इसमें मतलब कौन मतलब इसमें
Okay.
क्या होगा, ठीक है।
Okay,
ये
so
पूरा क्वेश्चनलेस वाला है, इसे पूरा पता है कि पूरा क्वेश्चनलेस है।
okay.
रिटेनिंग वाला क्वेश्चनलेस में है।
Okay, I have got your point. So the portion of layer 1 which is below the water table, so that will be under complete saturation, and you should use the saturated unit weight given to you for this portion. Okay, so this is
यस सर।
would be saturated. Now further
लेयर 1 के लिए ही सर मुझे अलग अलग 2 बार फाइंड करना पड़ेगा, उसके बाद लेयर 2 में जाना है, वही ना सर?
yes, but for layer 1 I don't know it will be under dry or some bulk unit weight is given to you, so you please cross check.
Not there is not any bulk unit, only a dry unit and a saturated unit is there.
Okay, then you can use the dry unit weight as the bulk unit weight of the soil of layer 1 above the groundwater table. Okay,
Then after we will go to the layer 2, na sir?
then using these two units, you have to first calculate the vertical stress, and if you know the vertical stress, then you can determine the horizontal stress by using the earth pressure coefficient and vertical stress. So if this is questionless, then for active condition, suppose for active condition we are assuming that, okay, not assuming because you are telling me that this soil is layer 1 soil is questionless, so this should be Ka times sigma p. Okay, now for layer 1, and obviously this sigma v will be effective. Please keep in mind. So for layer 1, so suppose we are basically trying to determining the active earth pressure at this level, just at the bottom of layer 1. So at the bottom of layer 1, what will be the value of sigma v prime? So we are assuming that this is the bulk density or bulk unit. So it will be 17 multiplied by 7.
एक्चुअली में सर हमें टोटल मुझे फाइंड करना है लेयर 2 तक के लिए ही सर, लेकिन प्रॉब्लम मुझे सिर्फ यही था, इसीलिए मैंने आपको लेयर 2 के बारे में नहीं बोला, इसका मतलब ड्राई यूनिट कितना है वो नहीं बोला।
No, you first please complete your problem statement na. Otherwise it will be very difficult. For what level you are trying to determine the active earth pressure or what?
Yes sir, I just want to layer first earth pressure.
So I am basically giving you an example how to calculate the active earth pressure. So if you know one example, then you can easily follow that procedure and you
Yes sir,
can
yes
complete
sir.
for the whole problem na.
Okay sir.
So it's very
Then after
difficult to
17
solve
into
a
7.
problem completely. Okay, so for each layer, considering the time bound of this problem or this kind of session, it's very difficult that for each individual layer we should basically go for the calculation and let you show the entire part. Okay, so right now I am giving you the example for the interface that is at a depth of 9 meter
Okay,
from
sir.
the top surface. So 7 meter, this is under, for that we'll use the bulk unit weight, and for the remaining 2 meter, so this 2 meter we'll use the submerged unit weight. And since the gamma sat value is given to you as 16.5, I don't know whether these two values are feasible or not, because saturated unit weight, as per my understanding, it should be a little bit higher as compared to gamma bulk, whatever the situation is. So if we basically assume the unit weight of water as 10 kilonewton per meter cube, so gamma submerged will be 16.5 minus 10, that means 6.5 multiplied by 2. So this, after calculating this value, this will give you the sigma v prime at the interface. Now you try to determine the sigma h. Now what will be the sigma h? So sigma h would be Ka sigma v prime. This is due to the overburden, means from the soil, and additionally you have to consider the earth pressure which is coming from the water table also. So water table effect you have to consider, and it will be only for a height of 2 meter. So that means there will be gamma w multiplied by 2. So this will give you the active earth pressure at the interface between these two layers, layer 1 and layer 2, though I don't know what are the properties of layer 2. Okay, and I don't know what is the phi value of layer 1, because to calculate the Ka value, you should first know about the friction angle or properties of shear strength properties of layer 1, and you didn't provide them. Okay. So I hope
सर
now
ये
on.
वैल्यू फाइंड करने के लिए सर एक ही लेयर में, जैसे कि वाटर टेबल भी आ गया है एक ही लेयर में, तो सर के अलग अलग फाइंड करना पड़ेगा कि एक ही के से काम चलेगा?
What is the basic expression of K? That you should know first. Okay.
Yes sir, 1 minus sin phi by 1 plus sin phi for active case.
Okay, then is it mentioned anywhere in the problem that you should consider different phi values depending on the location of water table? So some phi values above water table and some different phi values below water table.
No, sir.
If no, then you should consider one phi value for one layer irrespective of the
Okay
location
sir,
of
okay
water
sir,
table, and
I
you
got
should
it
be
sir.
having the constant
Okay
K.
sir,
Okay.
I got it sir.
Please don't unnecessarily complicate the problem statement. It's very straightforward. So the water table location will basically will have an impact on the vertical effective stress or the vertical overburden, effective vertical overburden. Okay. So your coefficient of earth pressure will only vary as soon as you are basically encountering a different layer. Different layer in the sense you are having different shear strength properties of the soil. Obviously pi, because this coefficient Ka, this is defined in this fashion. 1 minus sine phi by 1 plus sine phi. So you are having only one variable phi. So as long as phi is constant, you are having constant k, and if phi is
Yes,
different,
sir. Sorry, sir.
you will be having different k. Okay. Okay, so now may I solve this problem, problem 5?
Yes, sir.
May I solve, sir? Okay. Okay. So in this problem also two layers are involved. However, in this problem there is no such water table location inside the layer, and rather it's instead it's mentioned that the water table is at a great depth. So therefore you need not to bother about the water table. However, for examination purpose or for assignment problems, if you have the water table inside the backfill, so you please consider the water table impact or the effect of water table on the active earth pressure distribution or the passive earth pressure distribution, whatever the scenario is. Now in this problem, a 12-meter high retaining wall is given. Now this 12-meter high retaining wall supports a subsoil consisting of two layers. Okay, so this is your layer 1 and this is your layer 2. Now for layer 1 and layer 2, both are having equal thickness. So that means this is 6, okay, or rather I can mention it in this fashion: 0 meter, 6 meter, and 8. Now the properties are mentioned in this table. So for layer 1, C is given as 23 kPa, pi value is given as 15 degree, and gamma is given as 15 kilonewton per meter cube. For layer 2, this is a sand or cohesionless soil. So C value is 0, pi value is 35 degree, and gamma is 18 kilonewton per meter cube. So we are having two different layers. The first or topmost layer is cohesive frictional, and the bottom layer is purely cohesionless. Okay. Now what we have to determine? We have to determine the total active thrust acting on the retaining wall before the formation of tension crack. So as I mentioned at the beginning of this session, that considering the formation of tension crack before and after, will be having two different active earth pressure distribution behind the wall, and that we'll see through this numerical problem. So first of all, what we have to do, we have to basically calculate the individual coefficient of active earth pressure for each of this layer. So please cooperate with me and calculate the active earth pressure coefficient for layer 1 and layer 2. So Ka, we can calculate from this equation: 1 minus sine phi by 1 plus sine phi. So therefore, considering the notation Ka1, so this represents the active earth pressure coefficient for layer 1, and Ka2, this represents the active earth pressure coefficient for layer 2. So please let me know what are the values of Ka1 and Ka2 with the given properties of layer 1 and layer 2. Please cooperate with me, okay? So for the first layer, it would be 0.59, and for the second layer, I hope this would become 0.27. So these are the two active earth pressure coefficients for layer 1 and layer 2 respectively. Now we'll basically follow this active earth pressure distribution expression, that sigma HA gamma Z Ka minus 2C root K. Okay. Now first of all we will consider layer 1. So layer 1, for layer 1 at Z equals to 0, your sigma HA, it will be simply minus 2C root K A1. Why? Because this Z now becomes 0. So therefore it would be simply minus 2C root under KAA. So therefore 2 multiplied by, what is the coefficient value of layer 1? 23, and the active earth pressure coefficient is 0.59. So quickly tell me, what is the value? So it will be minus 35.33. Now we'll discuss about the determination of tension crack depth, that is Z equals to Z0. So we'll try to figure out the depth Z0, where, because, so simultaneously we'll try to draw the distribution. So first of all, at Z equals to 0, so we are having some negative pressure of magnitude 35.33 kPa. Okay, so this distribution is in kPa. Now as we go down or go in below inside the layer 1, so at a time, so this depth is basically at a depth Z0, the distribution crosses the line. Okay, that means the active earth pressure becomes 0. And we have seen already earlier that what is the expression of this Z0. So that this Z0 we can calculate in this fashion. So 2C by gamma root under Ka1. Okay, I am denoting 1. So this 1 subscript will indicate all the properties are for layer 1. Okay, so therefore it will be 2 multiplied by 23 multiplied by 15 multiplied by root under 0.59. So 46 divided by 15 multiplied by 0.59. So this will give you 3.99 meter as the depth of tension crack, or nearly 4 meter. Okay. So since there is tension up to a depth of Z0 equals to 4 meter, so this depth is also known as tension crack depth. So after this depth, the variation would be completely in the positive side. Okay. So at Z equals to Z0, how we have determined? We have determined by equating sigma HA equals to 0. By equating sigma HA to 0. Now we'll calculate the active earth pressure at the interface, that is Z equals to 6 meter. Now what will be the active earth pressure at the interface? So this will be gamma 1 Z into Ka1 minus 2C root under K1. Okay. So you can also use this as C1 because we are basically considering only the layer 1 right now. So this is C1. Now we'll substitute the values. So gamma 1 is your 15, Z is your 6, K is your 0.59 minus 2 times 23 multiplied by 0.459, or we can directly take it from this equation, that it's 35.33. Okay. So after calculation, so I think this would become 40. So am I correct? 15 multiplied by 6 into 0.59. 17.77. Okay. So 17.77. So we have got the value. So this is 4 meter. So suppose this is the interface. Okay. So this value we have got 17.77. Now, since we are encountering an interface at a depth of 6 meter, so we will be basically having two different okay, it's better to calculate in the next slide. So we will be having two different two different active earth pressure at the same level. So at Z equals to 6 meter. I hope one of you asked about this, na? That if, since the coefficient of earth pressure is changing at the same interface, so you will be having two different active earth pressure at the same level. So how we can determine this? So we can determine this. So sigma HA. So now onwards there will not be any cohesion component. So only the gamma to Z2 component. Okay. So rather here we can write in this fashion that gamma 1 Z plus gamma 2. Okay, so it will be difficult to write because this will be again, because the Z will now change. So rather we can write the final expression, that is 15 times 6 multiplied by K2. K2 what? 0.27. So I hope you may get this point. Okay, so this is the vertical stress. So this is the vertical stress multiplied by the active earth pressure coefficient of layer 3. Okay, so rather I think we can introduce two different notation, H1 and H2. So at this level this will be gamma 1 H1 AA, and here this will be gamma 1 H1. Okay, okay, now we'll move further. Okay, we'll calculate this value as well. So 15 times 6 into 0.27, so this will give you 24.3. Okay. So as you can see, at the second layer we'll be having slightly different active earth pressure, slightly greater. Okay, so this value is your 20. Now we'll determine this pressure at the base. So at Z equals to 12 meter, so sigma HA, this will be gamma 1 H1 plus gamma 2 H2 Ka2. Okay, so that means 15 into 6 plus, what is the unit weight of layer 2? That is 18. 18 into 6 multiplied by 0.27. So 90 plus 18 into 6 multiplied by 0.27. So this will give you 53. So this value is your 53 point. This is positive. Okay. So in this way, we can complete the active earth pressure distribution behind the wall. And please note a few things, that since in this problem we didn't encounter any water table, so wherever you will basically have some water table inside the backfill, so you will also calculate the active earth pressure at that level also. Okay, otherwise just at the top, bottom and at the interface, it will basically give you the a tentative distribution, because we know at the top it's having a minus value 35.33, at the interface for layer 1 it's 17.77, and for layer 2 it's 24.33, and at the bottom 53.46. so this is your layer 1 and this is your layer 2. Again, this is 0 meter, this is 6, so this is the active earth pressure distribution diagram. Okay, now we'll discuss about the formation of tension crack. Now, if the tension crack is not formed or before the formation of tension crack, so this will be the distribution. Okay, this is before formation of, or here we can write this is before, and here this is okay. Okay. Now, how it will modify if we consider the formation of tension crack? So this is for before the formation of tension crack. Now, once the tension crack forms in the top portion of this layer 1, so what will happen? The adjacent soil will be separated from the retaining wall. So there, since the soil is basically weak in tension, there will not be any touch. The adjacent soil mass will not be any touch with this retaining wall. So that means this part will not be there, because now the soil will not give any pressure, because the soil is not in contact with the wall. So therefore, the distribution will be modified in this fashion. So it will simply start from at a depth of 4 meter, and then it will vary up to the base of the wall. So this diagram is not in scale. Okay, so this is Z0, this is 17.77, and this is 24.33, and this is 53. Okay. Okay, and these are the elevations.
Sir,
Huh.
sir, let me show layer 2 calculation part.
Tell me.
Let me show your layer 2 calculation part.
Okay. Fine. Are you done?
Yes, sir.
Okay. So these are the two diagrams considering the formation of tension crack, that is before and after the formation of tension crack. Now, as per the problem is concerned, So we will have to determine the total active thrust acting on retaining wall before the formation of tension crack. So at least for this problem, we'll be bothered about this diagram, and we have to calculate the total active thrust, resultant active thrust. That means we have to take the area of these individual components. Okay, so suppose this is one component, this is component 2, means simple geometry. We are basically splitting the entire distribution into simple regular geometries. Regular geometries in the sense trapezoid, triangle, rectangle, and so on. So this is one triangle, this is triangle 2, and this is trapezoid 3. Okay. Now what we will do? So we'll basically, since we are not having any space, so here we will basically calculate that total active earth pressure PA, this is before tension crack formation, okay. So this value would be A2 plus A3 minus A1. Now what does it represent by A2, A2, A1 and A3? So A1, this is the area of triangle 1, A2, this is the area of triangle 2, and A3, this is the area of trapezoid numbered as 3. Okay, so it's very easy, so we can easily calculate. So first of all, we will basically calculate the area of triangle 2. So it will be 17.7. This is the base and the height is 2 meter. So this height is 2 meter. So half into 17.77 into 2 plus A3. This is the area of the trapezoid. So this will be this plus this, that means 53, two sides, summation of two sides divided by 2 multiplied by the height. Height is basically 6. It is 77. So 24.33 plus 53.46 divided by, okay, it's given, multiplied by 6, and minus half the upper triangle, that is 35.3 multiplied by 4. Okay, so in this way you can determine the, okay, you can determine the total active thrust which is basically acting on the wall before the formation of tension crack. Now please calculate and let me know. So first of all, I think it will be 17.77 plus how much you are getting. So I am getting something 180.48. Okay, this much kilonewton per meter. This is the, just let me cross check it once. 24.33 plus 53.46 into 3 plus 17.77 minus 35.33 multiplied by 2. Yeah, 180.4. So this is the resultant active thrust. Now I'll request you, so as per the problem statement, this problem is solved. Now I'll request you, so 2 homeworks will be there for you. So first of all, determine the PA value after formation of tension crack. Okay, So this is one homework. And second, so for determining the resultant active thrust, considering after formation of tension crack, this distribution you should consider. Okay, so there will not be this component minus 10 pressure will not be there, and then you have to determine the location of PA. Action of or locate the or locate the line of action of PA from base. Okay, and considering both the scenario, both scenarios. So this would be two homeworks for you. So this is, first of all, you have to determine the PA considering the formation of tension crack after formation of tension crack, and secondly, you have to locate the line of action of PA from base for both scenarios. Okay, is it fine? Yes or no? Okay, since there is no response, I am assuming that this is okay. So since we have already exceeded our time bound, so we'll start solving these remaining problems in the next session. So 3 more problems are there. So first of all, this problem 6 is basically interlinked with problem 5. So we'll basically take the same problem, problem 5, and now we'll consider that the wall is now moving in such a way that it mobilizes the passive pressure condition. So therefore, we'll try to determine the total passive thrust acting on the wall. So in the previous problem, we have determined the total active thrust acting on the wall before the formation of tension crack. Now, in this problem, we'll try to determine the total active thrust acting on the wall. And in problem 7, we'll basically try to determine the horizontal component of total active thrust for a retaining wall which is having an inclined backfill. Okay, inclined backfill. So right now, so far, we have considered that all the backfills are having a horizontal surface. However, in problem 7, we are having a retaining wall with inclined backfill surface, and for that, we'll try to determine the horizontal component of the total active thrust acting on the wall per meter length. So this is for problem 7, and this was the homework. Unfortunately, we couldn't solve all the problems which we have decided for this session. So we'll also try to solve this homework problem in the next session. So this is for today's session. Now we'll again meet on next Sunday, that is on 1st October at 5 p.m. And in between, the problems whichever we have taken from this week as the homework, so please try to solve those problems at your home and let me know about the difficulties. So we'll then end this session here. Thanks a lot for joining this session.